Our next lab project, beyond the basic momentary start-stop logic. In front of you is the basic start-stop logic. And just a quick review, we're using a true if on because remember, we're using a normally closed stop push button. And the reason for doing that is so it is fail safe. It fails in the safe mode. The safe mode for a motor is the motor not running. If we had a normally open contact switch, a normally open push button, then we would be using a true if off instruction here to show that the button wasn't pushed because the input wasn't on, so the button's not pushed. The problem is that if the switch fails, the stop switch fails, then it won't work. In other words, if you break a wire or the switch breaks and you push the button, nothing's going to happen. So we're using a normally closed push button for our stop push button. A normally closed push button, not pushed, the contacts are closed and the input is on. True if on, stop push button, meaning it's not pushed. And then of course we have a normally open push button for the up because we want it momentarily closed to complete the logical path to turn on this bit in memory. And then when you release the button, this bit is now on. We just turned it on right here. This writes to that bit and this reads that bit. So when you release the push button, you maintain logical continuity and the motor stays running. We did take and move the stop push button over to here simply to mix things up a little bit so you didn't get the feeling that the stop push button had to be first because it's more important. As long as it is in series logically with everything in this rung, the motor will stop when you push that button. We also changed a couple other things around just so you don't get to thinking that these instructions and that address memory locations have to be in a particular format. So I move this up to here and I move this down to here. So this logic is 100% identical to what we started with just a few moments ago. And it reads, if motor up bit is on, or if you're pushing the up push button and you're not pushing the stop push button, then energize the output and set out 00 on. And when you release the push button, input 4, by that time output 00 is on. So when it comes back and it scans the rung again, it reads it and it says if output 00 is on, or if you're pushing the push button. Well, you're not pushing the push button anymore, but output 00 is on because you turned it on. And if you're not pushing the stop push button, the rung is true and it turns on output 0. And remember that this rung executes thousands of times per second. It doesn't matter that output 00 is already on. It has nothing to do with it. The rung just is true, it sets the bit to 1. It's true, it sets the bit to 1. Thousands of times per second. When the rung goes false, it sets the bit to 0, thousands of times per second. Just something to keep in mind. So the next thing we did is we said, all right, we can start and stop this motor. Now, remember this is motor up, and we need a reversible motor for the garage door because we want to run it up and we want to run it down. So we have to be able to reverse the motor. If it were a DC motor, you would do that by reversing polarity. But this is an AC motor. And AC motors have other requirements to reverse them. Now, if it's a reversing single-phase motor, there's a capacitor involved. For a reversing AC motor, there's going to be at least third conductor, but that's not the only way to reverse an AC motor. We're doing a three-phase industrial garage door opener. Our AC motor is three-phase. And with three-phase motors, you just reverse one phase. And you do that by using a reversing starter. Now, a reversing starter actually has two starters. They're two 3-pole contactors, if you like, with aux contacts. And one of them, you have the phases and we'll just call it ABC, and then the other one it's ACB. It doesn't really matter which one you reverse. It could be BCA. But you reverse one phase and the motor goes the opposite direction. So this is our circuit that turns on the coil for a starter that makes the motor go in the up direction. So this output 0 doesn't go directly to the motor. The output terminal on the controller is not feeding voltage to the motor. It's feeding voltage to a coil that's part of a starter, or if you like, contactor. The difference between a contact and a starter is starters normally have overload contacts. Now we're not going to include that in this lab. Three-phase motor, two starters, basically contactors. One of them has one of the phases wired opposite of the other one. So this is our coil, motor up, output 0, for one of our starters that makes the motor go in the up direction. We can start this motor and we can stop this motor. We've demonstrated that. However, once you hit the motor up button, you could, I guess, stand there and wait till it gets all the way up and hit the stop push button. And you actually can do that on industrial garage door openers. You can hit up, and then when it gets up, say halfway, enough to let air in to ventilate the place, you just hit the stop button, it stops right there and stays. However, what if you want it to go all the way up? You want it to go up and automatically stop. That means that something has to know that the garage door has reached the highest position or the full open position. And you can do that with a variety of sensors. You could use a photo eye, you could use a proximity switch. However, traditionally it is a limit switch. And if you don't know what a limit switch is, it is a mechanical switch, usually with normally open and normally contacts. And the switch is operated by an axle. And the axle has an arm mounted to it, and that arm hangs down in the path of a moving object. And when the door gets all the way to the top, it hits the arm, the actuating arm, rotates the shaft, and flips the state of the switches. The contacts normally close, so they change state. What you would want to use in this case is the normally closed contact of a limit switch. Again, that makes it fail safe. So if the switch breaks, or the contact is broken, or the conductor is open, the motor is not going to run. And we're going to put that right here in series with the stop button, because they both effectively do the same thing. This switch, the normally closed switch that we're looking to see if it's on, to see that it's not pushed, if it opens, it drops continuity or logical continuity to the output. So we're going to add another true if on right here, and we can pick our tag from here. We would go to up limit switch, input 2, double click. Now we have it. Now I'm going to download this and go online. I'm going to pause while I do that. I find it interesting that we were looking at the sequence program when we downloaded, but it pops up with buffer inputs. No harm. I was just surprised that it didn't pop up with the same view we had offline when we downloaded. But I was surprised. So here is our static rung. Now there is one thing here that's not static. As a matter of fact, I could ask you this. Looking at this logic and understanding what these 4 bits are, you've got a stop push button, input 3, you've got an up limit switch, input 2, an up push button, input 4, then you have output 0, which is the motor up coil for the starter. What state is this door in right now? Not a trick question. I don't think it was in the manual necessarily at this point, but it really does. I think it is. It does ask whether the door is up or down. Now remember, this is when you look at what's true, pressing input 4, let's try that. See, input 4 went true, right? But the door's not going up. What's keeping the door from going up? That's right, the up limit switch. Well, since this is a normally closed limit switch, and if it were closed, the input would be on and this instruction would be true, this one, that means that that switch is tripped. The door is in the up position. To make this completely static, if I wanted to start the motor going up, I would have to move the door off of the up limit switch. In other words, I would have to run the motor down. I could flip on input 2, then we could start the door, run it until it hits the up limit switch. But instead what I'm going to do, I'm going to leave it right there, and we're going to add a second rung of logic for the motor down. Now in the manual, I ask you quite a few questions. The discussion that we're doing right now should answer all of those discussions without me saying, okay, on page 115, in step 5, it says, what is the garage door doing right this instant, judging by the state of the logic? How long will it continue to do what it is doing? Well, the answer to that question is, if you were looking in the manual for step 5, it shows that everything is true or on. In other words, the motor is running and the up push button is released, but the motor's running. Well, the motor's going to keep running until it hits the up limit switch, and then this instruction goes false. I'm not going to go through all of these questions step by step like that. But if you need to have the manual in front of you, and you can check your answers against my description and discussion of this logic, just like you would do in a live classroom. That's how I got started doing this. I originally wrote a manual that covered all 71 instructions for the Micrologics family. Well, Micrologics 1000. A book of lab projects. And I thought, okay, now what's missing here? For people who are doing this on their own at home, well, they need lectures about the technology. So I created a bunch of lectures which are on YouTube, and you can buy the hard copies on the website. And I said, okay, well that's nice. I've got lectures on the technology and lab projects. What's missing? Well, after each lab project in a real classroom, you would have a discussion. I'm going to add another rung of logic for motor down. In the manual, I had you do quite a few things with last man wins. In other words, you had the rung duplicated, which you would not do in real life. But I wanted to give you one more shot at understanding the concept of destructive bits, meaning if I have two OTEs addressing output 0, 0, one of them is going to dominate. In other words, if they're two identical rungs, well, then it really doesn't matter. Not so much, because both rungs are either true or they're both false, so they're not going to fight each other. But if I had two rungs that were both trying to control output 0, 0 and the logic was different, the last one in the order of scan is the one that would dominate. So I'm going to add the motor down rung, which really should look pretty much just like this. And to do that, I'm going to save and go offline. Save and then disconnect. Now we're offline. I wouldn't say that I was lazy, but I don't believe in doing things the hard way. I would pick that rung, Control C for copy, Control V to place it right below that one, just like you would with a word processor. Now I have two identical rungs. This is up and we want this to be down. Well, to change it, it's real simple. There is only one stop push button, by the way. We don't have two stop push buttons. So we don't have to change this, but we do have to change some of this. The first one that I would probably change would be, I would change motor up to motor down. If I click on this, I think it's output 1. Yep. So I would go over here, pick output 1. That one's taken care of. Stop button stays the same. Up limit switch. It's input. Oh, we want down limit switch. That's input 1. And we have a down push button. So down push button. Input 5. And that should do it right there. Here we have, if the motor's already energized, or if you're pushing the up push button, you're not pushing the stop button, and you're not all the way up, then run motor up. This one is if the motor is already running down, or if the motor's already on going down, or if you're pushing the down push button and you're not pushing the stop button and you haven't hit the down limit switch, then go on down. We're going to download that, and I'm not going to make you watch me download. Now we're back online. By the way, I've told you before, but I will repeat it again. I do not script these videos. I don't sit down with a manual and write a script for things to say. I just open up the manual, I start doing the labs on the screen, capturing what I have and passing on what I see in front of me that I think you should know and understand. In years past, I did try the scripting thing, and then I tried to go back and re-record things that I made little mistakes on, and the end result just wasn't as good. To include things that you think of on the spot, it just doesn't work well. Plus, every time I went back and re-recorded to remove an error, I put another error in there that wasn't before. However, I do go back and edit the audio and the video to cut out some of the hams and haws and so's and ands. And here we have our two rungs of logic. One to control the up motor starter and the other to control the down motor starter. And right now we're online and running. The stop push button obviously isn't pushed, that's why it's true. But notice that neither one of our limit switches are on because these are normally closed. One of the challenges of testing this logic is that you have to be really faithful in how you operate your limit switches. And what I mean about being faithful, testing this logic and how you operate your limit switches, is if you look at this logic right now, neither motor is running and you can't start either one. If I push the up push button, nothing happens. If I push the down push button, nothing happens. And I can't operate the limit switches. So what is going on here that is preventing us from running this motor up or down? Well, neither one of those instructions are true. And to be able to go up or down, one of them has to be true, input 1 or input 2. So we have a situation here where both limit switches, now remember that this is true if on for a normally closed contact of a limit switch, which means if the limit switch is not tripped, then the instruction would read it as being on and it would be true, and neither one is true, which means that neither limit switch is untripped. Not neither one is tripped, neither one is untripped. Now looking at the logic, I flipped on input 1, the down limit switch. Now does that mean that the down limit switch is tripped or untripped? Remember, it's a normally closed contact. So if it's a normally closed contact, that means that contact is the normal state, the switch not tripped. So right now the down limit switch is not tripped, so the normally closed contact has continuity, and input 01 is on, and this instruction is true. The down limit switch is not tripped, but the up limit switch is tripped, so that means that the door is all the way open. I had some other logic that I did in between where we began the garage door with the up-down rung and where we're at now. And that is, I said if we wanted to use the normally open contacts, in other words, if the switch is tripped, then the switch normally open contact is closed. In other words, instead of opening the normally closed and using that, we're closing the normally open and using that instead, which means that the input would be on if the door was tripped. Instead of off, it were tripped. So it would not be safe, wouldn't be fail-safe. And I had you go through and do a bunch of iterations with that logic, answer some questions so you could firmly see, some potential problems, but you could still do it that way. It just would not be fail-safe. So I did skip that and went right to garage door opener safeties, because these being normally closed limit switches makes the circuit safe. So right now we are all the way up because the up limit switch is tripped. The state that we were in before with input 1 in this state, this is impossible unless one of the limit switches or both of them are damaged. So we'll go back to the down limit switch not tripped. You could even change the terminology on that tag to be not down limit switch. I mean, it is the all the way down limit switch, but because we're using the normally closed contact, that tells us when it's on, it's not down. We cannot go up at this point. I'll push input 4, and you can see even though I'm pushing that button, because it's already up and it's tripped the up limit switch input 2, it's not going to run that motor up any further. Now if I push the down push button, 5, you see it goes true, and the rung stays true because now output 01 bit is on in memory, and it stays on because it says if you're on and you're not pushed the stop push button and you haven't hit the down limit switch, then turn the motor on. I mean, it was already on, and that's the first condition in that rung. What would happen the instant that that motor started to go down? In other words, you turn on the down direction of the motor, what would change immediately that you don't have control over manually in a real garage door opener? That's right, the up limit switch would immediately become untripped, and it would look like this. So when you see the logic in this state, the upper rung, you could actually press the up button right now and turn on that winding. That's another problem. We're going to deal with that later on in the lab. You could possibly apply power to both starters. I'll just go ahead and do that so you can see it's true. I'll push input 4. And see, now the motor's trying to go up and down. Now, if you know anything about three-phase motors, you would have some action. It would probably trip the overloads. The motor would not like this. So we can't allow this to happen. So I'm going to stop and then restart the down because that's what we were using. Remember, we went down and then we flipped input 2, the up limit switch. We changed it from being tripped to untripped, and now it's on. So that's what allowed us to hit the up button and then have the motor trying to go in 2 directions. Now we're going to prevent that later. But for right now, we want to keep it simple. To operate this right now manually, if you want to reverse direction, you have to stop it and then push the button in the other direction. If it keeps running like this, I mean, when you look at this logic, motor up is not on, the motor down is on. So what has to happen eventually? The door has to get all the way down, and when it gets all the way down, it hits the down limit switch and stops and stays right there. You can go up from there, so we'll push the up push button, and then as soon as the motor up direction turns on, we have to flip the state of input 1 because we've no longer tripped that switch. And now it's going to go up until it gets all the way up and trips the up limit switch and stops. It's that simple. You have to be faithful when you're doing these labs to operate the sensors that would react to the results of the logic. The results of this logic are these 2 outputs, motor up, motor down. That's all it does. If the motor goes up, it's going to hit the up limit switch. If it goes down, it's going to hit the down limit switch. If the motor's going up, then it's going to untrip the down limit switch and eventually trip the upper limit switch. If the motor's going down, it's going to untrip the up switch and eventually trip the down switch. We could write logic in the background with timers and then replace these up and down limit switches with bits that are controlled by timers to simulate a elapsed time between you told the motor to go down and the garage door actually gets down there and then opens up the down limit switch. We didn't do all that, but I did have you exercise this logic. Then I said to you, okay, well, we only have 1 stop push button. And you could leave your logic just like this. You don't have to change it to match that in the book. As you move on in your programming career, if you have an instruction that's common to both the up and the down, or to a function, you're not going to have 2 separate rungs. You're going to combine the 2 rungs into 1 rung and have that single condition, like the stop push button, affect everything else. So I'm going to go offline and I'm going to make those edits. Ordinarily, I might make some pause, make some edits, and come back. I'm not going to do that this time. Instead, in the manual, I had you move things around in a particular sequence. And I'm going to just do it without looking at the manual, and maybe I'll do something different so you can see there's more than one way to do it. But my goal is to get the stop push button out here and to branch around all of this. That will be the challenge because this branch around works a little bit different. So I'm going to put it there, and then I'm going to move, I need to move these 3 instructions inside between here and here. I don't know if I can drag this. Nope, won't let me drag it. With RS Logic, you could drag that. And that's why I'm doing it this way instead of following the steps in the manual. I'm going to force myself to go through the misery of doing this the first time. So I move that instruction over to there. I move this instruction over to here. Now this instruction, we'll try moving it there. Now see, that didn't work. So I'm going to go up and undo that. See, it made a mess. Instead, I'm going to put a branch around that and then bring this over here. And then delete this branch around. Now I need to get this logic, except for the stop push button, right here. So I'll delete the stop push button because I don't need that. And I'll just drag up see, we're getting close. Now I need a branch around this right here. So the focus is there. And then delete this. In the manual, I flip the push buttons and we'll call it the aux contact or the seal-in contact. I flip the positions around to what's more conventional. So I'm going to flip these around. So I'm going to move this up here. Move that down here, move this up here, and move that down here. So now I have the push buttons on top and the aux or seal-in contacts on the bottom. The last thing we did, or one of the last things that we did in that particular lab, was we eliminated the problem of both of those motor starters being energized at the same time and overloading the motor. So I added instructions, true if off, into each. Well, I guess we could select it from here. I don't want output 0 coming on if output 1 is on, right? In other words, if output 1 is on, you can't turn on output 0. So we'll do the same thing in the other half of this logical circuit, only we will pick the up motor. So now let's download it and check it out. Save, download, pause. Back online with our logic. Neither motor is running, so both of those conditions are true. True if off, output 1. True if off, output 0. Notice that the up limit switch is tripped. It's false. So you can't go up. You can only go down. Let's go down, and that is input 5. Now we're going down, and that's going to untrip the up limit switch. And we're going to stay in that state. Let's just look at it right there. You can see if I push the up button 4, see it goes true, but because we've already energized output 1, you can't energize the up motor. If the motor keeps driving the garage door down, eventually it will trip the down limit switch. And it'll stop. Now I had you do something where I had you push the up and the down button. Then I asked the question, untrip the down limit switch. Okay? This could be true if the garage door is somewhere in between. And of course, it pushing the up and the down together, no matter what I do, it's if the up motor was already energized, last man wins, so to speak. In other words, output 1 is off, so in the upper part of the rung, that's true, turns on output 0, and remember the logic reads left to right, top down. So no matter what happens, it's going to read the upper half of this before the lower half. If the upper half is true and turns on output 0, there's no way that the bottom half could turn on output 1. And that's pretty much everything that we did in that lab. We're not done with the garage door opener yet, but we wanted to keep these videos at a half hour roughly, no more than 30 minutes. We're going to stop this one and then start up with this project, garage door opener, in the next video.